So thank you very much indeed to the organizers for inviting me to give this presentation. I'm terribly sorry that I can't be with you in person in Bangalore today. I think the last time I was there was in 2007 when Rohini organized the wonderful linear collider workshop at that time. So I look forward to my next visit, but unfortunately it's not today. So it's my pleasure to give the status of the International Linear Collider and Compact Linear Collider projects. Linear colliders, as I'm sure most of you are well aware, are not new concepts for a future E+C- collider. The SLC ran at SLAC between 88 and 98, and then there were ideas for follow-on projects that eventually crystallized into the International Linear Collider that I'll say more about, and the Compact Linear Collider, which has been developed with a collaboration centered at CERN. This idea has been going since the 1980s. So linear colliders are very well studied concepts for a future high energy machine. So in this talk, I'm going to focus on the accelerators themselves. I'm not going to say anything about physics and detectors because you've heard a lot about that already. And what I'll try to do is to give an overview of both of these projects, some of the ongoing developments, the status of project preparation, and then a summary. So let me start with CLIC. So CLIC is envisioned as an electron-positron linear collider to be built at CERN for the era beyond the Hi-Lumi LHC. It's based upon a novel and rather unique so-called two-beam accelerating technique that I'll explain, and it's based on high gradient room temperature RF cavities. And the first stage, the Higgs and top factory stage of CLIC, is planned to be 380 GeV center of mass energy, and this would be a facility 11 kilometers long, and we would need roughly 20,000 of these expand cavities for it. It's intrinsically expandable. Of course, linear colliders are intrinsically expandable because you can always make them longer. And so the plan for CLIC is to start with the Higgs and top factory, and then if physics dictates, one could lengthen the facility and get to higher energies, in principle, as high as 3 TeV. So this is how that looks, the schematic. The first stage, the 380 GeV stage of CLIC, is roughly the diameter of the LHC. It's about 11 kilometers long. And then if one went to higher energy stages, you see here the footprint for 1.5 TeV and 3 TeV, which fits in the Geneva Basin, essentially running along the foot of the Jura. And there have been a lot of civil engineering and site studies done by the CERN civil facilities team over many years. So the conceptual design report for CLIC was published already 10 years ago in 2012, and we updated that in 2018 with the project implementation plan that was submitted to the update of the European particle physics strategy. And the cost was estimated at roughly 6 billion Swiss francs for the 380 GeV machine. And at that time, the power, wall plug power, was estimated at about 170 megawatts for 380 GeV. But in fact, this has been significantly reduced since this time, and I'll come back to that a little bit later. And of course, we did comprehensive detector and physics studies. So there are two collaborations that are pursuing CLIC, the Accelerator collaboration, roughly 50 institutes in 28 countries, and there's a detector and physics collaboration comprising 30 institutes in 18 countries, and you see the map of the various institutes here. The last time we met in person was in 2019, so I think for obvious reasons that I don't need to explain, we haven't been able to meet in person since then, but we are looking forward to a project meeting at CERN on December the 7th of this year. The project is extremely well documented, so I've just put here various links that you will find to the large documents that we prepared for the European strategy that cover the physics, the overview, the machine, and the detectors. And we've also made inputs to the SNOMAS planning process in the US. And again, you find at this page links to the accelerator, beam dynamics, the physics potential, and to detector studies. So let me move to the machine. So this is one of these busy tables with lots of parameters, but I just want to mention a couple of things. So these are the three energy stages, 380, 1500, and 3000 GeV. And the target luminosities in the design range from 2 to 6 times 10 to the 34 per square centimeter per second. If anybody's interested in any of these parameters, I can come back to them later. This shows a concept of the layout. As I mentioned, CLIC is a very novel concept because it's a two-beam accelerator. So one has a drive beam that comprises a rather low energy, less than 2 GeV, but very high current electron beam. And one then takes this drive beam and puts it through a series of decelerating sections. And by decelerating the drive beam, one can extract RF power at 12 gigahertz and transfer that power to the structures in the main beam. It's like a giant transformer. You have a low energy, but very high power, high current drive beam, and you use that to excite a low current beam to very high energies. And so this is the scheme for 380 GeV. There would be 8 of these decelerating sections, 4 for the electrons, 4 for the positrons. Here's the detector in the middle. And of course, there's an injection complex comprising sources, pre-accelerators, and damping rings, and so on. In the CLIC design, the baseline electron polarization has a magnitude of 80%. For 3TeV, it's conceptually identical, but different in a couple of details. So there are now 25 of these decelerating sections for the electron beam and 25 for the positron beam. And there are now 2 drive beam complexes, 1 for the electrons and 1 for the positrons. But in all other respects, the concept and the principles of operation are identical. So there is a large-scale facility, which is called SwissFEL, the Swiss free electron laser that I'm sure most of you are familiar with, which is running at PSI. And this is a system that comprises 104 2-meter-long C-band structures. So the frequency of C-band is roughly half that of X-band. So these structures are not identical to the X-band structures, but they're very similar. And the physical dimensions are within a factor of 2 in terms of apertures and so on. And so there's an equivalent length here of 800 CLIC structures that's been built and is working very successfully at PSI, and is accelerating beam to 6 GeV. So this is a large-scale system demonstrator for CLIC-like technology. The detector I'm going to say almost nothing about, but just to remind everybody that we do have a beautifully worked out concept involving an all-pixel silicon tracking system, a very highly granular calorimeter, a solenoidal magnetic field, and then a muon system based on instrumented iron. So where are we with the accelerator studies? Well, during this 5-year period that we're in, leading up towards the next update of the European strategy, there are really 3 areas that we're focusing on. One is the X-band technology itself, continuing to push the industrial design and manufacturing capability for these 12 gigahertz structures. We're looking at many applications of the CLIC technology, for example, compact free electron lasers, compact medical linacs, inverse Compton scattering sources, and so on and so on. And then on the technical side, we're pursuing a number of technical studies, including building a next generation CLIC module, of course, continuing to look at beam dynamics issues and understanding if we can increase the luminosity. And most importantly, looking at issues relating to power efficiency. So we're looking at high efficiency klystrons and looking at the whole footprint, energy footprint, carbon footprint of the facility to make sure that we can reduce that in the appropriate way. So the latest wall plug power estimate after a bottoms up rebaselining is about 110 megawatts of wall plug power for the 380 GeV machine. So that's considerably improved relative to the project implementation plan. It comes from a number of different sources that I can describe if anybody's interested. But efficiency is very important to us. And so we're now really pushing on these highly efficient klystrons up to 80% efficient. And these have applications at many, many future accelerators, including FCC EE, for example. So with the power wall plug power is 110 megawatts. This is fits very well within the current CERN site power capability, which is well in excess of 200 megawatts. And if you run for a snow mass year of order 10 to the 7 seconds. That gives you roughly 0.6 terawatt hours of electricity consumed per year. And that's about half of the current CERN electricity consumption. And as I say, further savings are possible through high efficiency klystrons. We're looking at the use of permanent magnets to replace electromagnets throughout the facility, and so on and so on. So the cost was also looked at again, and this is a table. The bottom line is that the cost of the 380 GeV drive beam based machine, as I mentioned, is roughly 6 billion Swiss francs with 20% error bars. We also looked, by the way, at the design of a klystron based machine. So this is an alternative, a conventional approach, eliminating the drive beam, which of course is one of the main features of CLIC. But if you say, fine, well, let's go to a conventional approach using klystrons only. And it turns out that that's much more expensive in today's understanding of the cost, and that's dominated by the cost of the main LINAC RF system, no surprise there, and it's essentially dominated by what one thinks the industrial cost of klystrons is today. And so that's something that I think faces many future accelerators. If you want large volumes of very complex systems such as klystrons, and you go to manufacturers today, you get an eye-watering price for what they think they need to supply them. But of course, if you were to industrialize that and you were to design a facility to produce thousands and thousands of them, then the unit cost would come down. But nevertheless, at today's pricing, the CLIC drive beam is by far the cheaper option than a klystron-driven alternative approach. We looked at other aspects of the cost, labor, the differential costs for going to the higher energy stages if one decides to do that, the costs of operations, and so on. Again, I can go into more detail if anybody's interested. So then, where are we now? So we're preparing what we call the project readiness report, which would be a step towards a technical design report. And we're targeting the period 25-26 for this next generation readiness report in time for the next update of the European Strategy for Particle Physics. We're focusing on the expand technology readiness for the Higgs and top factory 380 GeV first stage. We're focusing on optimizing the luminosity at 380 GeV, and we're focusing on power efficiency. So those are the ingredients that we will look at, and we'll issue our updated report in time for the next update of the European strategy. In terms of the timeline for the project, this is a notional timeline. It's a technology-driven schedule, not a resource-driven schedule. And so after a decision would be taken to start construction, we think we need roughly 7 years to build the first stage. That first stage at 380 GeV would then operate for of order 7, 8, or 9 years as determined by the physics needs. During that time, if one decided to go to higher energies, one could also be pursuing the construction of the stages at the ends to lengthen the machine. And then at some point, one would stop the running, and one would then need to connect up the extra stages to the 380 GeV stages with a downtime of order a couple of years, and then one would come back and run at higher energies, and so on if one decided to go up to multi-TeV. Now I should say that this is the schedule after a construction decision has been taken. I think it's no secret that at the present moment CLIC is somewhat on the back burner at CERN in terms of preparation, if you like it, Plan B, as Fabiola sometimes calls it. And so one would need to invest significantly in CLIC and spend something like 4% of the project cost in a 5-year readiness phase before one could really start the construction here. And so that would need a decision and investment if one decides to go in this direction. So let me then move to the International Linear Collider. So the ILC is also a very mature project. The technical design report was released almost 10 years ago now, in June of 2013. And at that time, the baseline machine was 500 GeV center of mass energy. And the cost estimate at that time in 2010 US dollars was roughly 6.7 billion, plus an additional 13,000 person years of labor. And you find the technical design report at the link here. Now, the machine that is on the table today is a 250 GeV center of mass energy machine. So it's the entry level Higgs factory, if you like. The length is shorter, it's 20 kilometers. And so the cost estimate for this machine is roughly $5 billion US. And the wall plug power is very similar to CLIC, actually. It's about 110 megawatts, and the total facility length is about 20 kilometers. So there's a lot of global interest in superconducting RF systems of the type that we want to use for ILC. Forgive me, I should have mentioned these are the niobium cavities, the superconducting niobium cavities. There are 8 cells there are 9 cells in a structure, and then there would be 8 of these structures put into a cryomodule. And so one would need roughly 8,000 of these structures. They're 1.3 gigahertz, and they would operate at roughly 2 Kelvin superconducting temperature. So there's huge interest in these systems. The European X-ray free electron laser is operating at DAISY in Hamburg. The LINAC coherent light source upgrade is being commissioned at SLAC. There's an X-ray free electron laser being built at Shanghai, and so on and so on. So I think people are probably very familiar with the European X-ray free electron laser, but here's a beautiful photograph of the LINAC. There are 100 of these cryomodules installed at DAISY, 800 cavities. The beam's been running since 2016, and you can think of this as a 10% scale model of the ILC. And so we're very fortunate that sitting in Hamburg is a 10% model of a future facility that we would like to build and operating very, very well. Now, of course, technology moves on. It's nearly 10 years since the ILC technical design report was released, and there have been many advancements made in the performance of these superconducting niobium cavities. There are new surface treatments and improved fabrication techniques that are leading to big improvements in the accelerating gradient, in the Q value of these cavities, in the yield for production, and improvements in the cost. So for example, the ILC specification is a gradient of 31.5 megavolts per meter and a Q value of 10 to the 10. And now the latest generation of cavities being produced at a number of labs using techniques such as nitrogen infusion have gradients of 45 megavolts per meter and a significantly higher Q value, which means you can operate them much more efficiently. So the technology is moving along a pace, and this is a montage. I won't go into the details, that shows many examples of how this technology is being used around the world. And here's another one. Again, I won't go into details unless people are particularly interested, but lots of labs, Fermilab, Cornell, JLab, Brookhaven, SLAC, Germany, France, Japan, and China, of course, really pushing these technologies. So there are extensive site studies for the machine in Japan. Studies have been done in the civil engineering, environmental issues, safety, and so on. And so the site, the candidate site in Japan, is near the towns of Kitakami and Ichinoseki. These are located just to the north of the main city of Sendai. So this is the footprint of the ILC in this region. It's basically sitting in a granite mountain, and it's rather robust with respect to earthquakes, because the entire granite mountain just goes up and down, and the accelerator really doesn't care so much. So there are engineering design studies being pursued for example, for the beam dumps, more work being done on the positron source and so on. At KEK, there's the Accelerator Test Facility 2, which is where we do studies of the final focus and the beam delivery system, looking at producing nanobeams. And we have a detailed plan for the 4-year work program to complete engineering prototypes and to complete an engineering design report. So this is another very busy table for the ILC parameters. Again, let me just guide you through a couple of important numbers. So the baseline machine is 250 GeV with a luminosity of 1.4 times 10 to the 34. There are a couple of rather straightforward upgrades. The first is simply to double the number of bunches in the RF pulse, which of course will double the luminosity. And the second is to increase the repetition rate of the machine from 5 Hertz to 10 Hertz, and this will further double the luminosity. So the cost of each of these upgrades is of the order of 5% of the baseline project cost. And so whilst every effort has been made in the baseline to arrive at the cheapest possible machine, in my opinion, spending an additional 10% to gain a factor of 4 in luminosity would be a very prudent way to go. But that's just my opinion. But these upgrades are really very straightforward and cost-wise rather cheap. There are also parameters for running at the ZPO, 91 JeV, with luminosities of order 0.4 10 to the 34. So this is not quite as high as FCCEE, but it would give you a sample of a giga-Z, 10 to the 9 Zs, in a couple of years of operation. And then, of course, most importantly, one can also upgrade to higher energies. So there are plans for an upgrade to 500 GeV, which would involve lengthening the machine from 20 kilometers to 31 kilometers. And then if physics motivates it, there's a further possibility to upgrade to 1 TeV, and that would involve lengthening the facility up to 40 kilometers. By the way, these lengths are based upon the design gradient of 31.5 megavolts per meter. If one decided to take a leap forward and adopt the higher gradient technologies as high as 45 megavolts per meter, then obviously one could get to these energies in a shorter machine, or in a machine of the same length, one could get to significantly higher energies, benefiting from the higher gradients. Again, just a word on detectors. There are two beautifully worked out concepts, the silicon detector SID and the large detector ILC, and there are international teams of people who've been developing these detectors over many decades, and they're beautifully designed concepts. So where are we now? Well, in 2020, ICFA, the International Committee for Future Accelerators, set up an international development team that was charged towards timely realization of ILC. And the IDT came up with a plan, 1 year of setting up, and then a 4-year so-called pre-lab stage prior to a decision on construction. And in this pre-lab stage, the idea is to finalize the technical prototypes, to prepare the engineering design report, to secure cooperation among the funding agencies, and to prepare for a construction decision and construction. So this is the organogram of the IDT under ICFA. I won't read out the names, but you see names of people you know in these various working groups. So there's a working group on setting up the lab, pre-lab, a working group on the accelerator, and a working group on physics and detectors. This is the accelerator working group. Again, forgive me, I won't read all these names, but there are people looking at the main LINAC systems, the damping ring, beam delivery system, and the beam dumps, the electron and positron sources, and civil engineering, and so on. So this team came up with a scope of the work that you would need to do in this 4-year pre-lab phase in order to be ready to prepare for the machine. And roughly speaking, you would need to spend roughly $60 million in terms of materials and facilities. And then you would need to spend a few hundred staff years getting to a point at which you are ready to take the construction decision. And this is not including work done on local infrastructure. So in response to the efforts of ICFA and the IDT, the Japanese ministry MEXT set up, reconstituted the ILC advisory panel that met between July of last year and February of this year, and they issued a report, which you can find at this link here. So they recognized the importance of the precision Higgs physics, which is of course very, very good news. However, they said that it was premature to transition to this pre-lab stage on the premise that Japan will express an interest to host the ILC. So forgive me, I can talk at length about this, but in my personal opinion, this is the famous chicken and egg problem. So Japan is not willing to indicate an interest to host until other countries indicate their willingness to participate, and other countries are not willing to indicate their willingness to participate until Japan makes a clear signal that it's prepared to host. So this is the chicken and egg problem that we have. Nevertheless, this advisory panel recommended that interested countries should continue to work on the technical issues, that one should decouple this technical progress from the thorny issue of hosting the machine, that one should continue to build relationships between the ILC community and the funding agency stakeholders, and that one should work with the funding agencies through reinforced collaboration and pursue the technical steps needed in a step-by-step process. So that's what we're trying to do at the moment. And meanwhile, locally in Japan, they have set up ILC Japan to coordinate activities among the community, local and regional authorities, the members of parliament and industry to promote the ILC project. So ICFA responded to all of these developments, and in April of this year, it reiterated its support for ILC. It extended the mandate of this international development team, further strengthen collaboration among the institutes, and expand support from the stakeholders. And ICFA continues to encourage intergovernmental discussions between Japan and potential partner nations toward realizing ILC. So what the IDT has done then is to identify what we call time-critical work packages, essentially to pull out the 2 years of really important things from this 4-year pre-lab proposal that was on the table, and then to figure out how we can make technical progress on these items while the thorny issue of discussions among funding agencies and so on continues. So let me, I think, move to my summary and allow time for questions. So ILC and CLIC are clearly technically mature projects. There are large X-ray FEL systems in operation using both of these technologies. The concepts have been really well developed over many decades. So the ILC TDR has been around since 2013, the CLIC CDR since 2012, and a project plan since 2018. Both of these projects are consistent with the European particle physics strategy, where the vision is to prepare a Higgs factory, an E+E- Higgs factory indeed. The European strategy explicitly recognizes that the timely realization of ILC in Japan is compatible with the European strategy, and that Europe would wish to collaborate if that goes ahead. So I think not only are both consistent with the European strategy, but both are affordable. So the costs of both projects are comparable with the cost of the LHC in today's money. The power levels are manageable. They're roughly 110 megawatts of wall plug power, which is rather similar to the LHC and well within the site power capabilities of the CERN complex. They're intrinsically upgradable for both luminosity and energy. And I genuinely believe that a linear collider offers a flexible and staged approach to the energy frontier. Of course, the energy achievable is directly proportional to the length, so it's adiabatically upgradable. And then one could always imagine that if you built a large facility, a large tunnel, and started off with ILC technology, if physics motivated you to go to multi-TeV scales, you could imagine reusing much of that facility with the higher gradient CLIC technology. And if, when the technology of wakefield acceleration is mature, you really wanted to go to many, many tens or 100 TeV scale collider, then again, you could reuse the facility for that. And this is all, of course, complementary to the long-term future for hadron colliders, or indeed other possible future colliders, such as muon colliders. So thank you very much indeed for your attention. I'll stop there, and I'm very happy to take any questions. Thank you.
Thank you very much. That's a very clear presentation, a lot of well-developed arguments, and we have some questions. Perhaps, actually, I give first the word to Rohini, and then we give the mic.
Just wanted to ask, since you made, okay, to begin with, thanks for getting up so early.
Pleasure.
Giving us this talk. You said that CLIC, for example, is 80% polarization from the beginning on the table. Can you, I mean, now since the FCC-EE will have so much more luminosity and, you know, even in the gigaZ, it becomes almost teraZ now. So in terms of the advantages of the polarization, can you make some statement whether it is still competitive or that advantage is now not there, whether that ship has sailed?
No, I mean, so the electron polarization, of course, is in a way a done deal, because that was already achieved at SLAC back in the 80s. So I think one would certainly have polarized electron beams at both ILC and CLIC. I think at a 380 GeV Higgs and top factory, the main advantage of the polarization, of course, is that if you run with the right polarization combination, you can get a significant increase in the luminosity. So basically, if you run with left-handed electrons in that combination, then for free, you get a higher luminosity because of the way the couplings work. So we would definitely plan to have it. It would give you this boost in luminosity. And of course, also at ILC, the intention would be to have positron polarization, which again, for a Higgs factory would give you a boost if you ran with the relevant handedness combinations of E+ and E-. And then I think, as everybody knows, if you're interested in future models of physics, of new physics, where particles come with left and right-handed labels, then it's a wonderful advantage to be able to do left, 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 right, right, left, and right, right spin combinations. Supersymmetry is, of course, the famous example that would benefit greatly from being able to control the polarization. But I think if one still believes that in SUSY-like models of new physics with left and right particles, then the ability to polarize the beam and change the polarization is a big advantage.
I guess what I was really asking is this gain in luminosity that one gets with polarization, effective gain. Now, compare that with the really much higher luminosities that a circular machine is going to give you. So I was wondering whether this advantage, which we all were very happy to think about in the years gone by, is that a real advantage even now? The physics point is well taken about, say, the nature of new physics. But this additional luminosity point that we all used to make, I'm just asking what is the strength of that?
I think since producing polarized electrons is demonstrated and is something that one can do, that one ought to do it. That's my own opinion, and it will give you the boost in luminosity. And it's, technically speaking, a very small addition to the technical complexity of the machine.
Okay, we have another question.
Yeah. Considering this high efficiency klystrons are based on this periodic permanent focusing, I understand, instead of the solenoidal focusing. So considering it is still in prototype state, so whether the industrialization is in line with the project timelines, because considering it is the permanent magnetic focusing, definitely there'll be a variation of the performance parameters in each klystron because of the limited constraints in the tuning.
Thank you very much. No, that's an excellent point. Forgive me, I'm not an expert on the klystrons myself, but my understanding is that 80% is achievable and has been achieved in the first prototype devices. So I appreciate that there's a step to go between first prototypes and industrial production, but my understanding is that the designs are very robust and that the first prototypes are extremely promising. And so, you know, if you allow 5 years, we certainly have 5 years, I think, before we will need large-scale series production of these things. And so if you allow 5 years 5 to 10 years for industrialization, I don't think that will impact upon the CLIC schedule.
Okay, thank you.
We have more questions. Over the seconds.
Yeah, so this may be a provocative question. So you mentioned about the plan B. So will the plan B always remain plan B, or there is any kind of point at which plan B can be upgraded to plan A? I mean, obviously I'm referring to CLIC and FCC, that connection. So
yes. So look, I mean, plan A for CERN is clearly FCC. That is the present plan. There's a feasibility study in place. You've heard all about it. You don't need me to remind you of that. So I think, were it decided at the next European strategy update, in light of the feasibility study for FCC, that for some reason one was not in a position to proceed with FCC, then of course you need to realize plan B. And so a CLIC is very much on the back burner at the moment. I mean, the CLIC project is being funded at a rate of roughly 5 million Swiss francs per year in the CERN medium-term plan. You do not get to a 5 billion project very quickly by spending 5 million a year. So obviously, we need the results of the FCC feasibility study to understand the facts and the science and the technical readiness of FCC. And then if for some reason it's not feasible, obviously the management at CERN and council and so on would need to take a decision to pursue plan B. And then you would really need to ramp up the resources for plan B, whether it's CLIC or whether it, for example, might be a muon collider, which is another plan B that's being pursued. So it's really a political decision that needs to be taken in light of the results of the FCC feasibility study.
Okay, we have, I don't know, you can manage. Thank you.
Thanks. This is a question about your future upgrades. When you lengthen the length of your collider, won't the curvature of the Earth be an issue?
Oh, no, that's a great point. So in fact, it turns out that the design of CLIC is for a laser straight LINAC, whereas the design of ILC is for a LINAC that follows the gravitational equipotential. The reason for that is basically ILC is a superconducting system, so you don't want all your helium, flowing downhill to the end of the LINAC. So it's designed to follow a gravitational equipotential. So in either case, of course, you have to take that into account when you extend the LINAC.
Okay, I think we had probably enough. I don't see any further questions. Thank you again, Phil, for a very good presentation.
Thank you very much indeed, Frank. Thanks to everybody for your patience. I hope it was clear. Thank you very much.
It was very clear. Thank you. Thank you.